Hey there, welcome to our deep dive into Grokking deep learning. You've given us quite the challenge with this one, a book that claims to make deep learning accessible, even if you're not a math whiz.
That's right. And we're going to unpack those core concepts, explore the code, and hopefully by the end of this, you'll feel like you've really grasped the essence of this, complex field.
The book starts with a fundamental question. How do machines learn? It's like, how do you teach a dog new tricks?
Think about it. You show them what to do, reward good behavior. Over time, they pick up the pattern.
Exactly. That's supervised learning in a nutshell. The book calls this teaching with labels.
The algorithm is given data that's already labeled with the correct answers, so it learns to map inputs to outputs, like predicting stock prices based on historical data. The algorithm learns from past trends to make predictions about the future.
Now, what about unsupervised learning?
It's more like giving a kid a box of Legos with no instructions. They just start building and figure out their own patterns and creations.
I love that analogy.
In unsupervised learning, the algorithm is given data without any labels. It has to find its own structure and meaning within the data, like grouping similar words together based on how they're used in text.
So it's more about uncovering hidden relationships.
Right.
And then there's this whole parametric versus non-parametric thing. That one was a bit tricky for me at first.
Think of parametric learning as having a set of knobs that you can adjust. You tweak them based on the data you have, try to find the best settings.
So you're essentially working within a predefined structure with a fixed number of parameters.
Exactly. Now, non-parametric learning is like having the ability to add new knobs as you learn more. It's more flexible, can adapt to more complex patterns in the data.
Got it. So you're not limited by a fixed set of parameters.
Yeah.
The model can grow and evolve as it learns. Okay, so we've covered the different ways machines can learn. Now, how do they actually do it? Chapter 3 introduces the heart of it all, neural networks. These are the things that make deep learning, well, deep.
They're like these intricate webs of interconnected nodes, kind of like the neurons in our brains. Each node receives input from other nodes, processes it, and sends an output to other nodes. It's this flow of information through the network that allows it to learn. And the book starts simple, showing how a single-layer neural network can predict something basic, like a baseball team's chance of winning.
Right. But it breaks down the code step by step so you can actually see how the prediction is made. What stood out to me was how they use these things called vectors and matrices.
They might sound intimidating, but they're just ways of organizing numbers. Vectors are like lists of numbers, and matrices are like tables of numbers. They're essential for handling the massive amounts of data that neural networks process.
Okay, I'm starting to see how it all fits together.
Yeah.
So we've got these neural networks, but how do they actually learn from the data? That's where Chapter 4 gets really exciting.
It introduces the concept of gradient descent, which is like the engine that drives the learning process. It's all about finding the best combination of weights and biases for the network to make accurate predictions.
The book uses this brilliant analogy of an archer aiming for a target.
I love that analogy.
The network is like the archer, and the error in its prediction is like the distance between the arrow and the bullseye. The network wants to minimize that error, so it adjusts its aim by tweaking its weights and biases.
Exactly. And gradient descent provides a way to calculate the direction and amount to adjust those weights and biases. It's like the archer getting feedback on each shot and adjusting their aim accordingly.
So the network is constantly refining its aim, getting closer and closer to the bullseye.
And this process repeats over and over, with the network gradually improving its accuracy with each iteration. And as the network learns, it's essentially building a mathematical model that captures the relationships in the data.
It's like figuring out the underlying equation that governs how the inputs relate to the outputs. Now, Chapter 5 takes things up a notch by introducing multi-input and multi-output networks. This is where we start to see the real power of deep learning, right?
Absolutely. This is where we move beyond simple predictions to tackling more complex tasks, like image recognition. The book uses the MNEST dataset, which is a classic challenge in deep learning.
It's a collection of thousands of handwritten digits that the network has to learn to identify. And what's amazing is that these networks can actually learn to see patterns in the pixels, just like our brains do. It's like they develop a kind of visual intuition for recognizing different digits.
And what's even cooler is that we can visualize the weights of the network and see how it learns to recognize specific features in the pixels. It's like peering into the mind of the machine and seeing how it represents these abstract concepts.
Now, Chapter 6 takes us on a journey to build our first deep neural network. We're not just talking about a single layer anymore. We're adding more layers, more complexity, more depth.
And this is where things start to get really interesting because we introduce the concept of nonlinearity. Without nonlinearity, adding more layers wouldn't actually make the network any more powerful. It would just be like stacking linear functions on top of each other.
It's like trying to build a complex structure using only straight lines. You'll hit a limit pretty quickly. So nonlinearity adds curves and bends to the network's thinking, allowing it to model more intricate patterns in the data.
Exactly. And the book uses a fantastic example to illustrate this. Predicting whether it's safe to cross the street based on a pattern of streetlights, a single layer network might struggle to learn the complex relationships between the lights. But by adding a hidden layer with nonlinearity, the network can start to capture those more nuanced patterns.
It's like the network is learning to reason about the situation, taking into account multiple factors to make a more informed prediction. And this brings us to Chapter 7, where we take a step back to appreciate the art of neural network architecture. It's not just about throwing more layers at a problem. It's about designing the right structure for the network to learn effectively.
Exactly. It's like being an architect. But instead of designing buildings, you're designing the blueprint for an artificial intelligence. This chapter is all about understanding how the flow of information through the network shapes its learning process. And one of the key concepts here is correlation summarization. It's a way of thinking about how neural networks learn by finding and creating correlations between the inputs and outputs.
The network is essentially looking for patterns and connections in the data, and the architecture of the network influences the kinds of correlations it can discover.
So a well-designed architecture helps the network focus on the important signals in the data while filtering out the noise. It's like designing a building to maximize functionality and minimize distractions.
That's a great analogy. Now we've got the architecture down. But how do we ensure the network is learning the right things and not just memorizing the training data? That's where Chapter 8 comes in, tackling the challenge of overfitting.
Overfitting is like a student who crams for a test and aces it, but then can't apply the concepts to anything else. The network might achieve high accuracy on the training data, but it fails to generalize to new, unseen data.
And that's a big problem because we want our models to be able to work in the real world, not just on the data they were trained on. So how do we prevent this overfitting from happening?
The book introduces a couple of powerful techniques: regularization and batch gradient descent. Regularization is like adding constraints to the model, preventing it from becoming too complex and overfitting the training data. It's like telling the student, don't just memorize the answers, understand the underlying principles. And batch gradient descent is about processing the data in smaller chunks instead of trying to swallow the whole thing at once. It's like training for a marathon by doing shorter runs instead of trying to run the whole distance on day one.
Now, Chapter 9 gets a bit more technical, diving into activation functions and how to model probabilities. This is where the math starts to creep in a bit more, right?
It does, but the book does a phenomenal job of making it accessible. Activation functions are basically mathematical functions that add nonlinearity to the network's calculations. They're like adding a bit of spice to the network's outputs, allowing it to model more complex relationships.
Okay, so instead of just having linear relationships between the inputs and outputs, we introduce these nonlinear activation functions to add more flexibility and expressiveness to the network's thinking.
Exactly. And the book introduces different types of activation functions like sigmoid, tan, and softmax, each with its own unique properties and applications.
I found the concept of softmax particularly intriguing, especially how it's used to model probabilities in classification tasks.
Softmax is like a translator that takes the raw output of the network and converts it into a set of probabilities that sum up to 1. It's like saying, given these inputs, here's how confident I am that the output belongs to each of these possible categories.
So if we're trying to classify handwritten digits, the softmax function would take the network's output and say, okay, I'm 90% sure this is a 7, 5% sure it's a 1, and 5% sure it's something else.
Precisely. And this probabilistic interpretation is crucial for many real-world applications of deep learning, where we need to know not only the most likely prediction, but also the level of confidence in that prediction. This is all starting to come together beautifully. Now, Chapter 10 introduces convolutional neural networks, or CNNs, which are specially designed for image recognition.
CNNs are a game changer when it comes to processing images. They're inspired by how our own visual cortex processes information, using filters to detect specific features, like edges and corners.
I loved how the book walked through a simple CNN implementation in NumPy, showing how these filters are applied to the image data to extract meaningful features.
It's a brilliant way to understand the underlying mechanism of these powerful networks.
And it highlights how CNNs can learn to recognize complex patterns in images by hierarchically building up from simple features to more abstract representations. Chapter 11 takes a detour into the world of natural language processing, or NLP.
Can neural networks actually understand human language?
That's the million-dollar question. This chapter explores how to represent words as vectors and use neural networks to process and classify text.
It's like teaching the network to read and interpret human language, which opens up a whole new realm of possibilities.
The book uses the example of predicting movie review sentiment, whether a review is positive or negative, to illustrate how neural networks can learn to capture the meaning of words and sentences.
And it dives into the fascinating concept of word embeddings, where words with similar meanings have similar vector representations.
It's like creating a map of the semantic space of language, where words are clustered together based on their relationships to each other.
So instead of just treating words as isolated symbols, we're now capturing their underlying meaning and how they relate to each other within the context of language.
Precisely. And this semantic understanding is crucial for tasks like machine translation, text summarization, and even chatbot development. Now, Chapter 12 takes us on a wild ride into the world of recurrent neural networks, or RNNs.
These are the networks that can process sequences of data, like sentences or time series, right?
Exactly. RNNs are like machines with a memory. They can remember previous inputs and use that information to influence their current output. It's like reading a book, where each word builds upon the meaning of the previous words.
The book shows how to train an RNN to generate text that sounds surprisingly Shakespearean. It's mind-blowing to see how these networks can learn to mimic the style and structure of human language.
And this is just the tip of the iceberg when it comes to RNNs. They're used in a wide range of applications, from speech recognition to music generation to stock market prediction.
Chapter 13 takes a meta turn and shows us how to build a deep learning framework from scratch. This is like becoming the architect of the architect, right?
It is. It's a deep dive into the nuts and bolts of how these frameworks work under the hood. It introduces the concept of autograd, which is basically automatic differentiation, a crucial tool for calculating gradients in neural networks.
This chapter really made me appreciate all the work that goes into building the frameworks we use every day, like TensorFlow and PyTorch.
It's like peeking behind the curtain and seeing the intricate machinery that makes all the magic happen. And it also highlights the importance of understanding the fundamental concepts of deep learning, regardless of the framework you're using. Now, Chapter 14 revisits RNNs, but with a twist tackling character-level language modeling.
What's the difference here?
Instead of predicting words, the network now predicts characters. Think of it like autocomplete on steroids.
So instead of trying to predict the next word in a sentence, we're trying to predict the next letter, which seems like a much more granular and challenging task.
It is. And the book introduces the concept of truncated backpropagation, a technique for training RNNs on long sequences of data without running into memory issues.
So it's like breaking down a long text into smaller chunks and training the network on these chunks sequentially, allowing it to learn long-range dependencies without getting overwhelmed.
Exactly. And this technique is crucial for many NLP tasks, where we need to model the flow and structure of language over long stretches of text. Chapter 15 takes on a topic that's increasingly relevant: deep learning on unseen data.
How is that even possible?
This is where we enter the realm of federated learning, a groundbreaking approach to training deep learning models without actually seeing the data. It's like a team of detectives working on a case without ever sharing their notes directly.
And the book dives into some seriously cutting-edge cryptography techniques like homomorphic encryption and secure aggregation. It's like deep learning meets spycraft.
It is. Federated learning allows us to train models on sensitive data that's distributed across multiple devices, preserving privacy while still benefiting from the collective intelligence of the data. It has enormous potential for applications in healthcare, finance, and other fields where data privacy is paramount. And finally, Chapter 16 wraps things up with some practical advice for anyone who wants to continue their deep learning journey.
It's like a roadmap for aspiring deep learners, encouraging you to start a blog, implement academic papers, contribute to open source projects, and build your network in the deep learning community.
So it's not just about learning the technical skills, it's about becoming part of the larger community and contributing to the advancement of the field.
Exactly. Deep learning is a rapidly evolving field, and the best way to stay ahead of the curve is to actively engage with the community, share your knowledge, and collaborate with others. This book has been an incredible journey, taking us from the fundamental concepts of machine learning to the cutting edge of deep learning research.
It's a testament to the power of clear explanations, intuitive analogies, and hands-on code examples. And it leaves us feeling not only informed, but inspired to continue exploring this fascinating and transformative field. Now, what were some of your favorite parts? Any aha moments that really clicked for you?
For me, that analogy of adjusting the knobs in Chapter 2, that really clarified the difference between parametric and non-parametric learning.
Yeah.
It's such a simple but powerful way to visualize how those approaches work. Parametric models are like machines with a set number of knobs, and you're trying to find the perfect combination of settings. While non-parametric models can add new knobs as they learn, making them more adaptable to complex data.
Exactly. It's like having a toolbox that can expand as you encounter new challenges.
And speaking of clear explanations, Chapter 3's breakdown of a simple neural network, that was a great starting point. Walking through the code step by step really helped me understand how the inputs are processed and transformed to produce an output.
The baseball team prediction example. That was perfect for illustrating the basic mechanics of a neural network. Shows how factors like the team's win-loss record and the number of fans in the stadium can be combined to predict the likelihood of winning.
Yeah, and the way the book explained weighted sums and activation functions, like, it made it all click for me. It's fascinating to see how these simple mathematical operations can be chained together to create a system that can learn from data.
Absolutely. And that brings us to Chapter 4 and the mind-blowing concept of gradient descent.
I still can't get over that Archer analogy.
Oh, it's so good.
It's such a perfect way to visualize how the network adjusts its weights and biases to minimize error. It's like the network is constantly getting feedback and refining its aim to hit the bullseye.
And what's incredible is that this process happens automatically, like guided by the math. The network doesn't need someone to tell it how to adjust its weights. It figures it out on its own based on the gradient of the error function.
Chapter 5's exploration of multi-input and multi-output networks really opened my eyes to the power of deep learning, tackling the MNIST dataset. That was a great way to see how these networks can handle complex, high-dimensional data like images. And the fact that we can visualize the weights and see how the network learns to recognize features,
Yeah.
it's mind-blowing.
It's like we're getting a glimpse into the network's brain and seeing how it represents the world.
Chapter 6's deep dive into nonlinearity. That was a bit more technical. But the streetlight example made it all crystal clear. It showed why simply adding more layers isn't enough.
Yeah.
You need nonlinearity to capture those complex relationships in data.
Exactly. It's like the difference between drawing a straight line and drawing a curve. A straight line can only represent a limited range of relationships, but a curve can capture much more nuance and complexity.
In Chapter 7's exploration of neural network architecture, that felt like stepping into the role of an AI architect. Designing the structure of a network to optimize its learning process it's such an intriguing challenge.
Yeah.
It's like you're creating the blueprint for how the network will think and learn.
And the concept of correlation summarization really highlighted how the architecture shapes the network's ability to find patterns in data. A well-designed architecture helps the network focus on the important signals and ignore the noise, just like a good architect designs a building to maximize functionality.
But even with a great architecture, we still need to be careful about overfitting, which Chapter 8 tackles head-on.
Mm-hmm.
I appreciate how the book emphasizes the importance of generalization, ensuring that the network can perform well on new, unseen data.
Yeah.
And the techniques for preventing overfitting, like regularization and batch gradient descent, those are essential tools in any deep learner's toolkit.
Right. Regularization is like adding guardrails to the learning process, preventing the network from becoming too complex and overfitting the training data. And batch gradient descent is a clever way to process the data in smaller chunks, which can help the network learn more smoothly and efficiently.
Chapter 9's exploration of activation functions and probabilities. That took us deeper into the mathematical underpinnings of deep learning. But even though it got a bit technical, the explanations were still surprisingly clear and engaging.
The different types of activation functions, like sigmoid, tan, and softmax, each have their own unique flavor and purpose. And the softmax function's ability to convert raw outputs into probabilities is crucial for many real-world applications where we need to quantify uncertainty.
Chapter 10's introduction to convolutional neural networks, or CNNs, that was a real eye-opener for me. The way these networks use filters to detect features in images, it's inspired by how our own brains process visual information. And the hierarchical learning process, where simple features are combined to form more complex representations, it's a testament to the power of deep learning.
CNNs have revolutionized image recognition, and they're now used in everything from self-driving cars to medical diagnosis. It's amazing to see how a technology inspired by the human brain can now outperform humans in some visual tasks.
Chapter 11's foray into natural language processing, or NLP, showed how deep learning can be applied to the fascinating world of human language. The idea of representing words as vectors, capturing their meaning and relationships in a multidimensional space, is just brilliant.
Yeah, it's like creating a mathematical map of the semantic landscape of language. And this semantic understanding is crucial for tasks like sentiment analysis, machine translation, and text summarization.
Chapter 12, Exploration of Recurrent Neural Networks, or RNNs. That was another mind-blowing experience. These networks have a kind of memory that allows them to process sequences of data, like sentences or time series. The example of training an RNN to generate Shakespearean text, that was both hilarious and impressive. It shows how these networks can learn to capture the style and structure of human language.
And RNNs are used in a wide range of applications, from speech recognition to music generation to stock market prediction.
Chapter 13's deep dive into building a deep learning framework from scratch. That was a bit intimidating at first, but it was also incredibly rewarding to get a glimpse into the inner workings of these powerful tools.
The concept of automatic differentiation, or autograd, it's like a mathematical superpower that enables these frameworks to train massive neural networks. And understanding how these frameworks work under the hood gives you a deeper appreciation for the complexity and ingenuity of deep learning.
Chapter 14's exploration of character-level language modeling with RNNs. That took us to an even more granular level of language processing. Predicting characters instead of words is a challenging task, but it allows the network to learn more nuanced patterns in the language.
And the technique of truncated backpropagation. That's essential for training RNNs on long sequences of data without running into memory issues. It's like breaking down a marathon into shorter sprints, allowing the network to train effectively on large amounts of text.
Chapter 15's exploration of deep learning on unseen data with federated learning. That was truly cutting edge. This approach allows us to train models on sensitive data that's distributed across multiple devices without ever centralizing it. And the cryptography techniques used to preserve privacy, like homomorphic encryption and secure aggregation, those sound like something out of a spy movie.
They do. Federated learning has the potential to revolutionize fields like healthcare and finance, where data privacy is paramount. It's an exciting glimpse into the future of AI, where we can unlock the power of data while respecting individual privacy.
And finally, Chapter 16's practical advice for aspiring deep learners was a great way to wrap things up. The book's encouragement to engage with the community, contribute to open source projects, and keep pushing the boundaries of deep learning. That was truly inspiring. It's a reminder that deep learning is a rapidly evolving field, and the best way to stay ahead of the curve is to be an active participant in the community.
This deep dive into Grokking deep learning has been an incredible journey.
We've covered so much ground, from the fundamental concepts of machine learning to the cutting edge of deep learning research. And I feel like we've only scratched the surface of this vast and fascinating field.
Yeah.
There's so much more to explore, and I'm excited to see what the future holds for deep learning. Now, let's shift gears a bit and talk about some of the broader implications of deep learning. This book, it really opened my eyes to the potential impact of deep learning on our world. It's already transforming so many industries, from healthcare to finance to transportation, and it's only going to become more pervasive in the years to come. So what are some of the ethical considerations we should be thinking about as deep learning becomes more powerful?
That's a crucial question. As with any powerful technology, there's the potential for both good and bad. One of the biggest concerns is bias. If the data used to train a deep learning model is biased, the model will inherit those biases.
Right.
For example, if a facial recognition system is trained on a data set that primarily includes white faces, it might perform poorly on faces of other races. That's why it's so important to ensure that the data we use to train these models is diverse and representative of the population. Another concern is job displacement. As deep learning becomes more sophisticated, it's capable of automating tasks that were previously thought to require human intelligence. This could lead to significant job losses in certain sectors.
Yeah.
But it's important to remember that deep learning can also create new jobs and opportunities. It's all about how we adapt and prepare for these changes.
Right.
And then there's the question of transparency and accountability.
Hmm.
Deep learning models can be incredibly complex, making it difficult to understand how they make decisions.
Hmm.
This lack of transparency can be problematic, especially in high-stakes applications like healthcare or criminal justice.
Right.
We need to develop ways to make these models more interpretable and accountable.
So it's not just about the technical advancements, it's about ensuring that we use deep learning responsibly and ethically.
Exactly. Deep learning has the potential to solve some of the world's biggest challenges, but we need to be mindful of the potential risks and work to mitigate them.
This book has given me a newfound appreciation for the power and complexity of deep learning. It's a field that's constantly evolving, with new breakthroughs happening all the time. And it's clear that deep learning will continue to shape our world in profound ways. What are your final thoughts for our listeners who are just starting their deep learning journey?
Dive in with curiosity and enthusiasm. Don't be afraid to get your hands dirty with the code. There are so many resources available online, including tutorials, courses, and open source projects. And most importantly, connect with other learners and share your knowledge. The deep learning community is incredibly welcoming and supportive.
This is just the beginning of an incredible adventure.
And remember, deep learning is not just for math whizzes. Anyone can learn it, regardless of their background.
So, what are you waiting for? Start Grokking Deep Learning today. That's it for our deep dive into Grokking Deep Learning. Until next time, keep exploring, keep learning, and keep pushing the boundaries.